Oh, my time is gone. So we're starting our unit 4, which is the organic. One thing I want you to keep in mind is the changes to the study design. So if you see a little bit that you don't understand, keep checking with that study design with those weird crossed out. We're a bit, I don't know why they did it, but they've got bits of various different things. It's only really in food they've gone, we're taking that whole kind of dot point out. So you have to check. That's why it's going to take me a bit of a time to really put together some of these questions, because I really have to double check. I can't just go in like I'd normally go and go and do it kind of like that. I've got to double check they're not going to mention some stuff which is going to freak you out. Right? So that's where we are. So we're starting with just looking at carbon, and why we love carbon so much is because it can make so many different compounds that we can use for different things. So they can be used for fuels, like we saw in our last unit, so we can be burning them, and that's just when we're looking at hydrocarbons. So it's just hydrogen and carbon bonded together in all these long chains and side chains and rings and all that kind of thing, but they're going to be just hydrocarbons, so just hydrogen and carbon. Now we're moving on to more of the functional biology kind of based chemistry, so it's going to have nitrogen in there, oxygens, alcohols, amines, sugars. We're going to start looking at more of a range. We've got maybe chlorines for our halo alkane. Why can't I say hello? Anyway, be thankful you don't have to pronounce anything. So we're going to start looking at all this thing. Why carbon is great is because of these 4 bonds. It means we can have almost infinite, I would imagine, if you look at it. So amount of arrangements. And what we're going to do is we're going to start looking at bond strength. So bond strength is just thinking about how our bonds change. So if we've got different atoms, depending on how far apart they are from each other, and depending on their electronegativity and the size of them, means how easy they're going to be to pull apart. The easier they are to pull apart to form reactions, that means they have a lower energy. And the further apart they're going to be, so if these are further apart, they're going to be easy to pull apart because they're not very well bonded, like the center of them isn't very well bonded to each other. But if they're closer, they're going to be harder. And if they're double bonded, they're going to be harder to pull apart. I'm going to put into the into our document, into our lesson, just a little table, because I think it's much easier to think about it if you can look at it like that rather than just randomness. So we've got bond strength, and as they get further apart, easier to pull apart. But we also have to think about in terms of our whole molecule. So if we've got lots of side chains, if we've got a really long molecule, it's going to be harder to do things with and pull apart than maybe if it was very short. And we can see this in some of our physical properties, which we're going to do on Friday. So how those physical properties change, so our change length and everything go. So next point, I'm scooting through this, but a lot of it I think is kind of revision, half this and the other. Isomers. So there's lots of talk about isomers in the books. The only thing you need to know is structural isomers. And these are the ones we did before. So these are the ones where I could give you, it's got this many carbons and this many hydrogens, and there's all those different ways you can talk about, side chains. That means it's going to be different from if you just have a straight chain. I might say it's got an alcohol group in. Well, you might choose to put the alcohol group on one end, or you might put it in the middle, and that changes the naming. It's going to change some of the properties of that organic molecule, but it's not going to be the same as with our lock and key mechanisms and our chirality in terms of trans and cis. So that's all you need to know, and it's the one we covered last year. So it's just understanding that if I say it's got so many carbons and so many hydrogens, that's really not telling you anything about the structure of it. And once we start changing that structure of how those carbons and hydrogens are arranged, that's going to change some of its properties. So thinking of structures, we're going to look at our representing. So there's different ways we can represent it. I'm going to expect you to be able to do all of them. Vika is going to expect you to be able to do all of them. And I don't. Oh, there's better. Right. So we have these in the data book. So if you're stuck and you can't remember which one, perfect. It's in there for you. You don't have to think about how to do it. You don't have to think. You do have to think. But you don't have to worry about which one's which. I can't remember. Who knows? How do I know? It's all in there. So the first one we have is our molecular representation. And that's just how many carbons, hydrogens, and oxygens are in there. Good for working on the molar mass, good for maybe having a vague idea of what kind of thing it is, but you don't know what this arrangement is, you don't know how it is, and I bet if I gave you this, you could all think of something different how we arranged it. So that's just our molecular arrangement. So I've written not useful. It is kind of useful, but it doesn't tell us the whole detail. Then the next one I'm going to is semi-structural. No, not structural. Let me get these. Structural. Doesn't look right, but it is right. So, how many carbons have I got? I've got 4 carbons. And I've got 4. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2. Yep. So this is our structural. So it's kind of that space filling model that you will very often see when you see the fancy drug design and things. There's a big talk among chemistry teachers who are more I want to say more chemistry than me, but they come from a different, more pure chemistry background maybe than me, who's had to use it and stuff. So they've been going on about they don't like this one. They like the one where it's showing the angles. So it's a bit more like that. But I don't like that one. I think it gets messy after a while. I think it all just looks a bit weird. And the book and Ed Rollo and Vicar seem to show them just like this. I think this is fine. I think otherwise you get confused with where you are and what you're going. So this is our structural. We can go from our structural to our semi-structural. This is the one I've been using the most, kind of in my biochem stuff I was doing. Maybe when you weren't doing the fitting models and stuff, but this gives you this information and then it gives you a bit of information about where everything is. So semi-structural is taking that one and kind of explaining it in our formula. So we've got C4H8O2, and what we're doing is we're condensing our structural to just say, okay, we've got a CH3 on here, a CH2, and a COOH, and from that gives us a lot more information. You can also have CH3, CH2, this one I've not seen so commonly. Yeah, that's a bit better. This one I've not seen so commonly, but this is another way you've done it. So saying we've got a CH3 on this end, we've got 2 of these here, and then we've got this one here. This would be much more common maybe if you've got a very long molecule with just lots of these in the middle. And it's the same. Then our skeletal. So our skeletal is the one you would have used the least up to now. I don't think we did a lot of them, but it's about taking this information and making it the most simple we can. So looks a bit alien. 1, 2, 3. Look at me. Carbon. There's a carbon. There's a carbon. Right. So when there's nothing labelled here, that means there's a CH3 because it's the end. Then this one with nothing labelled, you know it must be a carbon with 2 hydrogens because it's in the middle. And another one, a carbon with 2 hydrogens in the middle. Then this one, right? Yeah, okay. Yep, that is right. This one is a... I shouldn't do this on a Sunday. I'm losing my mind. So this is another carbon here. It's got a double bonded to an oxygen, and then it's got a oxygen and a hydrogen on the other bond. So 1, 2, 3, 4. So these are all our little carbons. So those are our 4 different types. So that's the first bit. So carbon, we love it. This is how we can represent it, and we need to start thinking about bond length. We'll come back to that when we look at properties.